Hi everyone, in this video we're going to look at example 2 in section 8.3 on series of real numbers. So in example 2, we're asked to discuss the convergence of this infinite series. Okay, so again, to get started, let's go ahead and just write out some of the terms of this series. So when n equals 1, we have 1 over 1 plus 1. When n equals 2, 1 over 2 plus 1. When n equals 3, 1 over 3 plus 1, and etc. So we can write this as 1 over 2 plus 1 over 3 plus 1 over 4. And when I see that, hope you caught me. The top number we have is 1. So the first one would be 1, second 2, 3. And as we continue down here, this should be 1 over 2, 2 over 3, 3 over 4, 4 over 5. Okay, etc. Cool. So right away, nothing jumps out at me to determine what this series converges to if it does. So again, to get a handle on that, let's look at partial sums. See if we can find any patterns in the partial sums, or see if we can determine if the sequence of partial sums converges. So what do those look like? Well, S sub 1 is just the sum of my first term, so that would just be 1/2. S sub 2 is the sum of my first two terms. So we have 1/2 plus 2/3, which is 1.17 if we calculate that out. I'm just going to write a little barrier here to keep our work separate. Now partial sum S sub 3 would be 1/2 plus 2/3 plus 3/4. So we can calculate that out and you can check my work, 1.92. So here are what our partial sums are looking like. 1/2, 1.17, 1.9. So we're growing by some amount each time. But just looking at the first three terms or three partial sums, it's not enough for us to determine what these values are converging to. So let's look at some larger partial sums or partial sums with more terms. So let's look at S of 100 terms. So again, I used a different computer program to compute that partial sum for us. And again, if you are curious, I encourage you Google around, find your own calculator or program that can do that for you. And you can check my work when you're doing that. But so the partial sums with the first 100 terms is going to be 95.80. S of 101, so if we add one more term to that, we're just going to add on the 100th and one term, so 101 over 101 plus 1. So we add 101 over 102 to that. And when we do that, we're going to get 96.79. When we add one more term, so S 102, we get 97.78. So again, so far we can look at this and ask, is it clear that these numbers are going to some number? I mean, maybe we think, oh, maybe they're going close to 100, but still we're already at the 102nd partial sum and we're not getting there yet. Another thing we can do is just look at how these numbers, these partial sums, grow as we continue to add one more term. So notice 95.8 to 96.79, that's about a growth of +1. 96.79, 97.78, that's also about a growth of +1. In particular, it looks like 0.99 is how much we're adding. Okay, that could be peculiar. So then we could ask, well, what's the impact of adding one more term? Does this pattern continue? Does this pattern where we're seeing the partial sum increase by 1, does that continue? Well, to get a sense of that question, we can look at what the terms are approaching. So we can look at the limit as n goes to infinity of n over n plus 1. So the terms of the series itself, what are those terms approaching? So as n goes to infinity, that numerator is going to go to infinity. That denominator is going to go to infinity. So we're going to use L'Hopital's rule here. So that's going to tell us this is equal to the limit as n goes to infinity of the derivative of n is just 1. Derivative of n plus 1 is also 1. So these terms, the limit of the terms themselves goes to 1. So what does that mean for us in this series? Well, that means that if we consider what this series looks like, so the limit, or that rather the sum, n equals 1 to infinity. So again, we saw this as 1/2 plus 2/3 plus 3/4 plus 4/5. As we go large enough, so as we look far enough in our series, we're going to just start adding ones. So eventually we'll just keep on adding ones forever. So if that's the case, what do we think the result of that infinite series is? Are we going to get convergence, or will this series diverge? Well, if we keep on adding 1, which is very much an amount, we're not going to be able to settle on just one fixed limit when we keep on adding more ones. So what does this mean? So in terms of partial sums, so this means, so for large enough n, so for the large enough term, the partial sum, so for S sub n, will increase by 1 for each term we add. So if we want S sub n to go to some number, well, that's not going to work out, because then if we just take the next partial sum, S sub n plus 1, we're going to get that number, that's 1. We're going to keep increasing by 1. So maybe to say a little bit more, since we eventually add 1 an infinite amount of times, our series will also reach infinity or blow up. In other words, diverge. Okay, that kind of got smushed in the end there. But what's really cool is that this is actually a theorem, which is a statement that can help us prove and determine whether or not a series converges or diverges. So this theorem says the following: if the terms in your series, so those terms themselves that we're adding up, does not go to 0, then the series of infinite terms, n equals 1 to infinity of a sub n, must diverge. Okay, so if the limit of these terms does not go to 0, then, so therefore that arrow implies that series diverges. So we might consider kind of the reverse question. So what about if the limit as n goes to infinity of a sub n's, what if it actually, this term goes to 0? Then does this mean that the infinite series, n equals 1 to infinity, a sub n converges? So no, that is not the case. So caution, no, that's not the case. What is the case? Well, it just means that it could converge or it could not converge. So I'll write that out. So if the limit of the terms go to 0, then this sum from the sum of the infinitely many a sub n terms converges or diverges. So what? So we need a new test and more info. So we need a different approach to determine if that series converges or diverges. All right, great work going through example 2. And I just want to emphasize again, this is our kind of first divergent or convergent theorem for this section. So we're going to collect a lot of different theorems and statements and facts to help us determine if a given series converges or diverges. And here's the first one in our toolbox. Awesome. Great work, everyone.